So this is Bobby. Hey, snap. So Bobby is the Director of Data Science at Dell Elastic. Sorry.
Little change recently.
He's going to be talking today about ProblemChild. And take it away.
Oh, great.
At the snap.
Yeah. Oh, before I've said anything. Great. Yeah, so my name's Bobby. Recent transition from Endgame to Elastic. My talk is on ProblemChild, which is a framework that myself, David French, Hiram Anderson all worked on to discover anomalous parent-child relationships. Now, before we dive into like the core framework, I want to take you back to a simpler time. The summer of 2017, a bit of ransomware kind of hit, and mainstream media, the security industry, freaked out. Understandably so. It was ransomware. It was bad. Took advantage of a particularly nasty SMB vulnerability. But what was more interesting is what it did post-exploitation. It carried out a series of adversary kind of tactics and techniques using seemingly benign software that came with the operating system. So self-execution, scheduling tasks were carried out using WinMic and scheduled tasks. And this rise of what the media started calling lol bins or living off the land kind of put the security industry in a peculiar spot because we had, both through technology and the will of marketing, started championing next-gen AV. And next-gen AV is great. We work on it at Endgame/Elastic. But if it doesn't catch this, then what do you need to do? And a layered defense is probably the most pragmatic approach. But what would that layered approach be? And the security industry rallied very quickly around something called MITRE ATT&CK. If you haven't been to RSA or Black Hat, go to any security vendor's website and you will see it en masse. And what MITRE ATT&CK did is they started to break down these potential adversary tactics and techniques into simplified categories. Spear phishing, self-execution, cred dumping, whatever. And the security industry, and specifically threat researchers, took this as an opportunity to build in this layered defense in the form of detectors or heuristics or rules, depending on what vendor you're talking about. And they did this using domain-specific query languages, whether it's Splunk, Elastic query language, equal, which is the example here. And it gave you a simplified way to express a potential adversary technique. A natural progression, and one that I think all of us here could certainly take advantage of, was the open source release of a series of red team and blue team frameworks. Atomic Red, Red Canary, Endgame put out RTA, MITRE, Caldera, Uber had one called Meta, and then blue team frameworks, which were made up of these kind of rule-based query language detectors for Atomic Blue, CAR, and Microsoft ATP queries. And that was great. It was the start of starting to be able to capture this sort of behavior. But as a data scientist, it was really a unique opportunity and a brand new data set that nobody here has really taken advantage of. 2 years ago, if you came, it was all DGA. Last year, a lot of Ember. Now I'm hoping, starting this year and onward, it will be more of like Windows events or auditd for Linux. A very kind of tricky data set, as you will come to find. And that was the impetus behind ProblemChild, this idea of applying machine learning not as a silver bullet, but as a way to help the threat researcher, security researcher, not necessarily catching everything, but reducing and ranking the amount of data that an individual who has to write these rules deals with. Instead of millions or billions of events, we're talking about hundreds, and in small clusters that folks can easily understand. And that's it. Machine learning to help people, kind of hopefully a novel take in the security industry. So what does that look like? This isn't open source yet, but literally if you follow these slides, you could build this today, maybe during lunch. It's really that simple. So what does data ingest look like? There are a variety of ways to get access to this sort of data. The sensor or collector, there's plenty of open source ones. I have WinLogBeat at the top, Elastic. Windows Sysmon, certainly readily available. OS Query, another good one. If you have budget, I'm supposed to tell you endgame sensors would be very good at this. But really, you just need a way to capture process creation and termination events. That's what we're really interested in today. Phase 2 may be a little more complicated. And the information you're seeking is there on the right-hand side of the slide. Now, having that information and then being able to do something useful from a machine learning standpoint requires a little bit of normalization and feature engineering. So we're just going to walk through this real fast about how you go from this really to this, something that we can train on, classify on. So we do a few different things from a normalization standpoint. File paths, because of the sheer amount. We do a couple of redaction steps using regex to wipe out drive letters and usernames. This is also good for maybe GDPR, to be determined, kind of on that front. Usernames, we're never going to capture every username in existence. So what we really care about is like, is it a system level username or is it not? Kind of a binary situation. Timestamps convert to an integer and then capture the difference of when the process was created and terminated. How long did it stay up? Capturing the relationship between parent and child process, we put in an embedding layer. It's about 100, a length of 100 of the most important Windows binaries we're interested in, and then one for unknown. It's a rudimentary way of doing it, kind of taken out of natural language processing techniques. And then for command line arguments, it's kind of the same idea, but we do TF-IDF to try to capture the nuance of flags, paths, arguments, and variables. And then we have a bunch of other questions we seek to answer with just really a 1 or 0 sort of feature flag. Is a process signed? Is the signer trusted? Give me the entropy of the command line, the entropy of the process name, the integrity level of the process being executed, and whether or not that was elevated. And when you have these features, you can start training a model. And this is beyond pedantic, but hopefully it gets the point across. Dataset into XGBoost, former endgame, we love XGBoost a lot. We use it a lot. And then once you have your inputs, you're feeding off the wire, whether it's SIM or just collecting it in bulk. Featureize it, and then you produce an output. Now the output isn't good or bad. We're more interested in the probability of it being malicious, some sort of float between 0 and 1. And we use that as our edge weight for a graph that we're going to build, because this is processes. Processes are trees. Trees are graphs. We're going to try to maintain all of that. So what does our graph look like? The graph is made up of nodes, and those nodes are unique processes, or PIDs. The edges are that creation event, parent spawns child. The weight of that edge, so the thickness of the arrow, kind of on the right-hand side, is the output from the model for that given event. And then metadata, which is kind of the rest of the event log. Once you have that, you have a weighted graph, and we can start to do some interesting stuff with it. Now, we did Louvain community detection to segment the graph quickly. You could do clique detection or spectral analysis. There's a bunch of different options there. We did Louvain because it's very, very quick. There are some problems here and there that I could address maybe during Q&A. But what this will allow us to do is take all those individual events and then attempt to collect them into an attack chain. Instead of just getting one bad thing, can we group an entire attack together? And that gives us our global view. It's what we at Elastic think is bad. It's based off of data that we have that could be biased. But anybody who's put a product out in a market can tell you that it looks amazing when it's inside your space, but the minute it goes to a customer, it blows up. And the first question is, well, why doesn't this work? Or, that's not bad, that's how my admin does it. Or, of course, random person has macros running everywhere. So we wanted to come up with a way to suppress potential false positives by giving it a local view. And we created something called a Prevalence service that really sought to provide a number that was in response to a question. So at first we looked at the probability of a process existing in their environment. So I've seen this process X% more than any other process. And then we normalized it into a quantile or percentile, however you want to look at it, between 0 and 99. And that was good, but it wasn't really descriptive enough to the problem we were trying to solve. So we moved to a more conditional probability of, from this parent, I've seen this child X% times more than other children from this parent. And that's huge, because SVC hosts spawning command line, that's kind of weird, but SVC hosts spawning something else might be extremely normal. And being able to capture that nuance will allow us to elevate certain things that are rare and suppress things that are more common in your environment. And something we're exploring now as we dive deeper and deeper into the data is kind of the same idea, but with command lines. So looking at a process and then looking at how rare or common a given command line is in that environment. So you can do a couple different things. From a threat researcher standpoint, you can answer some pretty obvious questions, how rare or how common something is. But for me, what I'm more interested in is reducing and ranking that data. So the application of the prevalence service kind of against that weight that we get from our supervised model will allow us to suppress commonly occurring things, which would most likely be false positives in this environment, and then rank order things that we find to be weird or anomalous. And that's it. I started to write this in pseudocode, and then I realized that I was just writing Python, so that's cool. Kind of a luxury of the language. But this is it. This is like literally the code to do all of this. So the slides are available, screenshot it, whatever. I encourage all of you to try this out, because it is extremely easy. You dive in with your weighted graph and a threshold that you could define, and I do a couple different things to define that. And then you perform community detection. As I said, we use Louvain. There's a NetworkX kind of Python library. It's import community, and then you're good to go. And then you iterate through each community in your list of communities, and then each node in your community, and you derive that prevalence score based off of the parent-child name. And then you subtract 1 and multiply that by the weight of the output of the supervised learning model to generate something aptly named anomalous score. Once you're done with a community, you take the max anomalous score for all nodes in that community, and if it's above a threshold, then we say that's bad. Set it aside, and we'll rank that when we're done and show that to the threat researcher. So that's it. That's ProblemChild. Very, very basic. There are hard parts, but it's almost all data related. Now, for experiments and results, what we wanted to do is we wanted to try to do this in a realistic setting, which is almost impossible, because we're not going to run APT malware in a corporate environment. So what we did is we faked it the best we could. Postmortem, red versus blue. We took the data that was available to us from the 2018 MITRE evaluation, which was APT3, which gave us 5 workstations. I'll go over that. But the model itself was trained on a bunch of data that you could go get today. Atomic Red Team has data. Red Team Automation has malicious data. Equal library has malicious data. And then getting clean Windows event logs is hopefully doable using your own machine or a couple machines kind of in your enterprise. And then honestly, the hardest part was detonating, executing kind of live malware, and then capturing it using sysmon or a winlog beat, whatever. So the threshold that I talked about determining which was good or bad, we did something that I stole from Phil Roth in his Ember notebook, is I just did leave one out retraining. So all those data sets that you see here, I would run one and then leave an entire segment of the data out, do it over and over and over again. And then I was looking at kind of a 2% false positive rate, which should make most people in here say that is not suitable for work. It's not. This is not meant to catch things. It's meant to help people. So we can deal with a little bit of frailty there. There were false positives. Like I said, things like admin-related PowerShell, people doing kind of odd things. Sometimes we would FP on that. FNs were mostly tied to not the process itself, but the support data that would come out of registry or DNS events that I just wasn't accounting for at the time. So we did that, and the threshold we came up with was about 0.37. That's what we kind of took to the APT3 emulation, which is, if you don't know, Chinese threat actor, pretty nefarious stuff, but they do a lot of living off the land. So it was a really good use case. MITRE, the way they emulated them was using kind of open source and COTS tools like PowerShell Empire, Cobalt Strike. There is some hiccups with doing this. There's not a lot of user noise at all. This is a evaluation sort of situation, so MITRE didn't have users on the keyboard the entire time, so that could make the adversary activity a little bit louder than normal. So diving into this, the data reduction part is kind of what I want to start with, because that's important, at least to me. So on each of these endpoints, and like I said, there were 5, there were about between 10 to 15 process creation events discovered. When we ran it through ProblemChild, we ended up with anywhere between 6 to 10 communities for each endpoint, which ended up being around, I'd say, 30 to 50 total events. So that's a massive reduction in data. It's then sorted and ranked and presented to the user like this, which hopefully you can see that. So what all did it actually kind of capture? From the MITRE attack standpoint, it was able to discover initial discovery techniques, so things like PowerShell, launching base64 encoded scripts that would do things like process discovery, system owner discovery, querying the registry, identifying different network activity. In ProblemChild, we were able to like pull that out and kind of group it all together. Not a singular thing, but the entire kind of attack tree. Likewise, it was able to detect more kind of sophisticated adversary behavior like lateral movement, where PowerShell script then tried to brute force Windows admin shares to discover valid accounts, and then do things like network share removal. And then finally, it was able to piece together actually multiple steps in kind of an attack chain. And this was a series of steps that MITRE performed that is a little bit more sophisticated. You can see there's a decent representation of binaries and processes being executed, doing things like creating a new service, masquerading as something else like Adobe Flash Updater, then executing that service, attempting to encrypt and compress data it was stealing, and then exfil it through FTP. Now that's great, but there were false positives. I put one meme in just now for Rich Harang, and that comes from the form of like repeated process calling process that happens sometimes, and we're not great at capturing that yet. More data, better labels will probably remedy that, and also just really weird command lines is problematic. So that's something to work for the future, but seemingly every endpoint would have 1 or 2 of these, and we're hoping that through like a web-based interface, a user can just say no, and then maybe active learning, we can kind of get better over time. So I want to highlight real quick the importance of like a prevalence service. Pre-prevalence, we were running into situations like this, a very benign activity with an extremely high score. According to our global data, this was bad. But the minute I put it in the MITRE environment and applied prevalence, it became quite apparent that this occurs all the time in their environment. So we were able to suppress those sort of false positives that would arise. And that's something that we'll kind of continue to refine over time. So what's next? Other than maybe DNS and registry and adding new events, one thing that I would really like to do for threat researchers is when we show them a cluster or community, we make recommendations on potential rules. It's like a template or Mad Lib style thing, and then query that automatically for them across their data set and say, here are the efficacy stats for this given query or rule. And that's it. Challenges, everything, kind of. Getting labeled data is extremely difficult. Realistic data is somehow even harder, and then trying to get diverse data is almost impossible without violating probably a lot of privacy rules and other things. So it's something we're constantly trying to tackle. Redaction of PII and looking at just internal endgame elastic user data will really go a long way in helping out. And then just not focusing on developers, because I sit next to developers or data scientists, but also admins and people in finance or HR, because we're all doing different things and we're all downloading things from different areas and we all have random crap running on our machines. And the more data we have and are exposed to, the better this sort of model will become. So that's it. There will be a paper, it's like 90% done, We had a couple of breakthroughs this week, and then just no time to update. So November 2019, I feel like I'm up here dropping my, my new album, but it'll be there. One of these at Filar, Threat Punter, Dr. Hiram will tweet it out or something, and everybody can read it. So, yeah, that's it. Thanks. Yeah, archive. Yeah.
Okay, quiz the guy.
Yeah. Just a single bead of sweat. Demo.
You'll be fine.
So I find this really impressive, building a view of the attack chain out of the process data. That's a really exciting development. And I agree, I think the prevalence service is key in denoising the crazy things that are on everyone's endpoints. I'm curious how you got participation in that. Was that hard to get people to tag for you what the prevalence was?
Yeah, so part of it we were able to do through some of these websites, some of these repos actually did a really good job. Then with the equal query language, for malware execution kind of in a live environment, how do you label, and this is a question that I told you to ask just in case, when you get that data back, there's benign activity and then there's just like a little sliver of malicious activity. So we used equal to pull out process tree information, and then we tainted the data set that way. So that's how we were able to do it. I think we're actively exploring a way for you to be able to do that in an open source method, because it is so hard. And we definitely struggled. At first we just blind accept, and we called everything from a malware sandbox bad, and then we were FPing on like task gen and a bunch of stuff that we shouldn't be. So we found that using equal in particular was able to pull out the data we were interested in. We could tag that, throw it back in, and call everything else benign, and the model improved greatly at that point.
Yeah, this is a great talk, and I kind of wanted to build off of that last question and this prevalence. How have you done studies on changing like the prevalence, like knowing when, okay, this is necessarily benign, or and how that affected your results?
So we have it,
okay.
And I do think something like that would be interesting because we take prevalence from the local environment. We are, I think, inherently blind on whether or not something's good or bad. We're taking commonness as a sign of more benign activity than probably malicious, which is maybe an inappropriate assumption, but it's all we got right now. So
sure, but how are you defining commonness? I think is more what I'm getting at.
Yeah, so we have like a threshold kind of set up that's like, if above, then we are more willing to call benign versus below, and that's kind of a fleeting thing depending on the amount of samples. And we kind of take it's like a law of averages across what we're seeing, which probably we've spent the least amount of time, I think, on this as far as applying it in the different ways, exploring different ways to apply it, which is something we desperately need to do, I think. And
one last little bit,
sure.
Do you update this like on like how often is this updated?
Yeah, so is data, the prevalence service, so take APT3, that data set. As we're predicting, we're also updating the service. So it's, if you think about it, streaming events, as data's coming in, that prevalence service gets updated as you're making predictions, because you're waiting till all data is ingested, in this case, because it's a post-mortem, to apply that prevalence service. So at that point, you have all the data that you just made a prediction on to say, okay, now that you made this prediction, how rare is it? So.
Thank you so much. As you mentioned, this is more of a post-mortem. Have you started looking into the evolution of the communities you've detected, or the dynamics of the evolution?
Yeah, so that's probably new job, new company is something that they're probably interested in, having a SIM and things like that. I think it'll be really interesting to look at both streaming data and then the evolution of those communities changing over time. Because we haven't really, we're looking at it in a moment in time, so we have no idea of like changes, like membership drop off or anything like that, to really understand how often you should kind of freeze a community to perform analysis, which again, like it's a data problem and it's just setting up the experiment probably in the right way, but something that would be fascinating to look at.
Yeah, great talk, thank you. So this reminded me of Polonium, which describes Symantec's file prevalence system. Like, it leverages basically the same guild by association thing. Like, have you looked into that? Have you considered differences between the community detection and belief propagation, for example? And
I didn't catch the last part, sorry.
Like, are you aware of that? Like
of
Symantec's? Of the Polonium and the guild by association idea? That
no, have not really explored that.
Okay.
But no, I'll catch up with you after.
Great, yeah,
to discuss that more.
To discuss more.
No, thanks.
Hey, could you talk more about the insight of the graph analysis?
Mm-hmm. Yeah, so the graph analysis part kind of came at the tail end. We were initially looking at a way to just look at data inbound, look at the events, and then just make a good bad prediction. But we realized at the scale that we were considering, it wasn't really useful to do just one-off events. So the endgame product actually has a little bit of a graph component to it already. So I started to think about that, and I'm like, all right, well, with Network X, I can represent each endpoint as a graph, and then attempt to derive more meaning or cluster more information together. And that's where the idea of applying that output from the supervised learning model as a weight in this graph, and then applying community detection kind of came into play. I still think there are probably, if not better, just different ways to do some of the graph segmentation. Like I said, there's probably a half a dozen just in Network X that you could try. So that's something I would encourage other people to explore as we internally kind of look at different options as well. I think there was one more, maybe? No? All right. Oh, yeah.
Thanks for that. So I'm curious about your thoughts when so ideally you have this malicious process being executed and you want to stop the execution before it completes. Otherwise you're already on. So thoughts about how to make that happen, like early stopping of
yeah,
activity.
So not this. You wouldn't use this. Yeah, that would be terrible. But what you would do is you would hopefully educate the people like my co-author David and some of the other folks that are writing detectors. So Red Canary's obviously really good at this. Endgame's quite good at this too. But what they do is they come across a sample and they fire it, and then they have to manually go through and start to pick this stuff out. And it's often like a one-to-one, which it's a lot like whitelisting or blacklisting a piece of malware. It's like, it's good, but wouldn't it be better if you could come up with a way to capture a bigger swath? And that's what we're hoping to do here, is just present greater communities based off of larger data sets that say, here's common malicious behavior that we've observed across n number of binaries. Can you write a rule to do this? And then obviously long term, I'll just call this Hiram work, would be figuring out a way to automate all that. Like, that would be amazing. So that's kind of where we're at. This, no, never use as like a way to stop anything. Please, yeah. So thank you. Good though. Good question.
I think on that we're out of question time.
And
so
lunch.
Thank you so much.
No problem. Thanks.